Welcome to the second lecture on Introduction to Algebraic Geometry and Commutative Algebra. In the last lecture you have seen definition of a affine algebraic K algebraic set. So, I will not recall much because after few algebraic preliminaries we have to again recall something. So, I will directly start with some topics which we will need more often later, which I will recollect now some of the basic stuff. So, this is rings and ideals. I will also be brief in this section because I assume that many of you are acquainted with these basic topics, but for the sake of completeness I will recall them briefly. So, as usual, ring that we recall last time, it has two operations, plus and dot. So, with respect to plus abelian group, with respect to multiplication it is a monoid and so on. So, I will abbreviate just this by A, and we saw in the last lecture, and as I said, always we will assume always commutative. That means this multiplication operation is commutative ring with identity, and the identity is denoted by 1 or 1 which is 1A. This will only we will use only this notation when there is a chance of confusion and there are many rings under consideration are involved. And then collection of all rings, that is I will keep denoting like this, rings with double underline, and of course we have ring homomorphism between the two rings. How do you compare two rings? Is a ring homomorphism, ring homomorphisms. Ring homomorphisms between the two rings A and B, just a map phi such that it should respect addition. So, I will write abbreviately and maybe talk more because we are assuming this, but for the sake of completeness we are recalling. It respects plus, it respects multiplication, and also 1 goes to 1. So, phi of 1A is 1B. This is also very important condition to assume. I just want to say one caution that some books they usually consider rings without identity and ring homomorphism may not map identity to identity, but we are not going to go in that generality because our main aim is to study rings which arise from algebraic geometry, and those are mainly polynomial rings and rings which are constructed from the polynomial rings. Okay, so, ring homomorphisms are defined. Then this set of all ring homomorphisms from A to B denoted by home is for homomorphisms, rings AB. This is the set of all ring homomorphisms from the ring A to the ring B. And I will just note here that rings with these ring homomorphisms form a category. So, this precisely in the due course I will make it more and more clearer. So, this right now just it is the objects. Whenever you have category, there are objects and there are morphisms and they set some properties. these two satisfy some obvious property. These properties I will recall in a due course, but in this case they are obvious. So, objects are rings, morphisms are ring homomorphisms, and some whatever obvious properties we will need, they are satisfied in this case. So, do not worry about it. So, before that there is a category of sets. The category of sets, objects are sets and morphisms are maps between the sets. Similarly, there will be groups and so on. So, category means two things: the data given is there are objects and there are morphisms, and this should satisfy some properties, and the properties are, for example, composition, identity map and so on. So, more and more when I need it, I will keep recalling it, so that this definition will become more and more precise. Right now we only deal with examples. So, now how do we know? So, the ring A, so this is ring. If you have seen in when you studied linear algebra, usually the base was a field. So, field, and what is the main advantage in the field? That it is a ring, of course, but every non-zero element has inverse, which is not true in the case of ring, because a typical example of a ring is Z. This is ring of integers. And polynomial rings. So, fields are usually denoted by K, L, etc. Rings are denoted by A, B, C, R, etc. So, this is the first example of ring. Also, another typical example we will keep using is Z modulo n. So, this is also ring. This is a finite ring and finite of cardinality equal to n. This is a ring in general, commutative. The operations are addition modulo n and multiplication modulo n. So, you add usually and divide by n and take the remainder, that is the definition of addition modulo n, and similarly multiplication modulo n. So, these rings are not fields in general, but you would have studied in your first course on algebra, this Z mod n is a field if and only if n is a prime number. So, we will have lots of examples of a field, but the real obstacle why algebra over arbitrary ring becomes more difficult than the linear algebra, that is algebra over a field, that is because the units may be too few. So, for a general ring A, I will denote A cross. These are all the elements in A such that A has inverse under multiplication. That means what? So, this means that is if and only if there exists B in A such that AB equal to 1 and also BA equal to 1. We do not have to say this because we are assuming the ring is commutative. So, this is obviously a group under multiplication. In fact, it is a subgroup of the monoid A dot. This is a subgroup. And this group is, this can be too small. So, for example, in case of Z, this is just 2 elements plus minus 1, and in case of Z mod n, it is just all those integers m in Z such that 0 less than m less than n and GCD of m and n is 1, co-prime integers in between 0 and n. So, this is called a unit group of the ring. This group is called unit group of A. The smaller the group it is, we will have difficulties in studying the equations. Alright, so this is about the ring. Now another last lecture we have mainly considered these rings, polynomial rings, kx1 to xn, polynomial ring in n variables. In this case, the units are precisely the constants, non-zero constants. So, the unit group does not change. This I will leave it for you to check. This is very important fact, we will use it again and again. So, there are not too many units. So, this will follow from the fact that if I have two polynomials f and g, then the degree of f times g equal to degree f plus degree g. These are if they are non-zero polynomials, both are non-zero, then this. Remember, I just want to remind you, reminder, degree of the zero polynomial is not defined. So, this is sometimes this is also called a degree formula. And this is more generally also true. Now, let me recall, I am just recalling these few facts from the basic algebra one has learned, recall from basic algebra. When do you call an A is a ring? When do you call then A is called an integral domain? If there are no non-zero zero divisors. So, what is a zero divisor? That is, there does not exist any A in A non-zero such that A times B is 0 for some non-zero B. So, such an element A, if there exists such a B non-zero and AB is 0, then A is called a zero divisor, and if there is no such, then you call it a. So, zero divisor by definition, zero divisor means an element A in A such that A times B is 0 for some non-zero B, then you call it a zero divisor. So, the zero divisors are the most troublesome because you cannot cancel them. Okay, so, equivalently, so an element A in A is a non-zero divisor if and only if non-zero A. If and only if the multiplication by multiplication by A, this is a map from A to A. This map is just simply any B going to A times B is injective. This is equivalent definition. So that's an integral domain. All right, the set of non-zero divisors. This is a very important set, as you will see in coming lectures. In the ring A is denoted by N Z D of A. This is a set of all non-zero divisors in A. In the notation, this is same thing as all those A in A, such that lambda A to A is injected. All right, once you say it is injective, A cannot be 0. Okay. So that is a set of non-zero divisors we will denote. Now the next thing, for example, in the examples, some examples. Z is an integral domain. There are no zero divisors in Z. That is obvious, because multiplication of two non-zero integers is again non-zero. Is one. Also, when is Z mod n is an integral domain? If and only if n is a prime number, if and only if Z mod n is a field. That is also clear from this middle one. But you can also nicely observe that this observation is very useful sometimes. A finite integral domain is a field. So proof: of course, field is always an integral domain. Field, everybody is a unit, therefore units are non-zero divisors. So I forgot to mention here, these non-zero divisors, set of non-zero divisors contains this unit group, because any unit is a non-zero divisor. That one can see easily from here. Okay. So proof of this. So suppose A is a finite integral domain. We want to show that every non-zero A, to show A belongs to A units. That is what we want to show. Because a field, if and only if the unit group is the maximum one, that is, in case of field, unit group is just removing 0, all the units are, that is all the unit group. So to show this, I have to produce, so AB, so I have to produce, so to look for B in A with AB equal to 1. B is because we are in a commutative case always. So how do you look for B? So look at this multiplication map by A. It's a map from A to A, and because A is an integral domain, every non-zero element is a non-zero divisor, therefore this lambda map is injective. but then it is a finite set. The map is from finite set to finite set, and then use pigeonhole principle to conclude this map is bijective. Therefore, bijective, write by pigeonhole principle. So, that means this is bijective means one is here, that should come from somebody. So, B has to go to 1, but where do B go? B goes to, by definition, A times B. So, we got 1 equal to AB, and therefore, it is invertible. So, we have proved that finite integral domains are field. All right. How do you now test somebody is a field or not? For that, I will introduce what are called ideals. Last time also briefly we have dealt with some ideals in some in connection with the affine algebraic K sets. So, let us recall what is an ideal. So, ideal in a ring. So, start with A is a ring, and a subset A, this is the Gothic A of A, is called an ideal if two conditions. Number 1, A with respect to the plus is a subgroup of A plus, subgroup, and second, for every A in A and X in A, X in the Gothic A times X, this is the multiplication in the ring, this falls inside Gothic. Then such a thing is called an ideal in the ring A. Ideal, to be precise, you could write in A. And usually I will denote in this course ideals by the Gothic letters like A, B, C, etc. P, M, etc. Initially it is difficult to draw, but certainly they are not as difficult as our Indian alphabets. Okay, so, and from the given ideals I will construct more ideals. Okay, now first how to give examples of ideals. So, some examples we should see. Always every concept should be followed by some examples. So, let us take very well known simple what we have worked with the ring A equal to Z, ring of integers. Or let me first take arbitrary ring. So, let us take a arbitrary and let us take an element. So, let A, fix an element A in the ring A. A is any ring. Now, what do? You take all A multiples of this small a. So, that means I am taking at all B times A, where B is varying in the ring A. For the obvious notation for this set, I will denote A times small a, simply because this B is varying. So, they are all capital A multiples of this. So, this is obviously a subset. Obviously, if I take two such elements B A and another one B prime A and add them, it is again of this form. This is B plus B prime A. See, you have used the distributive law here. So, therefore, this is closed under addition, and also it is closed under inverses because additive inverses, because minus of B times A equal to minus B times A. So, this is obviously a subgroup, and the second, so this we have checked this, and second condition is also obvious, because if I take any other C in A and any element B A in this multiples of A, then what is C times B A? This is nothing but, I will now put the bracket like this, C times B times A, and this is again of that form. So, you see we have all the things which are stated in the definitions are used. Okay, so, this becomes an ideal. So, there are lots of ideals in a ring. When does it become this ideal AA is usually called the principal ideal generated by A. This A is not uniquely determined by this ideal, because you see A and A minus A will also generate the same ideal. So, A times A and A times minus A, these two ideals are same. Okay. So, now you specialize A equal to Z, then all, in fact we can prove stronger than this, then every ideal in Z is principal, that is of the form Z times sum n, and we may assume that n is actually a natural number. If it is negative, then you replace by minus n, and then you still get the same ideal. And what is the advantage of this? Then this n is uniquely determined. In fact, n is the smallest, n is the mean among all multiples minus 0. Okay, so that is and we can imitate this process for 2 elements and 3 elements and finitely many elements, or even arbitrary family of elements. So, yesterday I did little bit, but now let us do it more precisely. So, this is, you call it, this is example 2. A is arbitrary ring, and let us take, first I will take only finitely many A12 AR, arbitrary R elements in the ring A, and then I want to write all A linear combinations of this A12 AR. So, that means I am considering the collection B1 A1 plus B2 A2 plus BR AR, where B1 to BR are arbitrary elements in the ring A. This is obviously a subset of A, and what is the suggestive notation for this set is A1 plus A2 plus AR, or when the ring is fixed ring and there is no confusion, this also we will write it as like this A1 A2 AR. Sometimes we can write A also just to remember the ring, but not necessary when the ring is fixed and when there is no chance of confusion. Okay, so again this is obviously an ideal, you have to check this is an ideal. So what will you check? You will check that this one is a subgroup under addition and it is closed under arbitrary multiplication by an element in A. So that I leave it for you, just imitate what we did it in case of one element. So this is called ideal generated by A1 to AR in the ring A, in A. Alright, now let us, in other words, so observe that this is very important observation, when you use it many times. This A1 to AR is the smallest ideal containing all these elements A1 to AR. Once it contains A1 to AR, obviously it will contain all the linear combination and it is the smallest, means this is ideal, so it has to be smallest one. So in other words, in the notation this means this is equal to intersection of A and this intersection is running over ideals A, ideal in A with all these A1 to AR belong to A. Obviously there is at least one ideal which contain all the elements, namely the capital A. So this makes sense. See, the problem will arise from set theory only when you have a set where there is the indexing set is empty set. Alright. So that is the smallest ideal containing this. Now if you have not finitely many elements but arbitrary family. So now I will write if AI I in I is an arbitrary family of elements in the ring A, then obviously now the other side is very good. Then the smallest ideal containing all these elements is called the ideal generated by A1 to AIs, and again we will denote it by this one, then this notation, all multiples of this and sum. This is by definition, this is the smallest ideal containing all AIs. That makes sense because there is at least one ideal which contain all of them, namely the capital A, and therefore the smallest makes sense, you take the intersection. But you can also describe like earlier description. So this is precisely the linear combination, but now when you say linear combination you have to take finite linear combination. So let me write precisely, this is set of all summation Bj Aj, where J index running in J, where J is a finite subset of I. If J is finite and these Bj's are elements in the ring A. So look at this finite linear combination, all of them, and obviously that forms an ideal, the same checking, and then this one. So, therefore, this is ideal, this is called ideal generated by the family AI. Okay, so just to one being little bit more sure, when do you call an ideal to be a non-unit ideal? A is called a non-unit ideal if this A is not the whole ring, then you call it a non-unit ideal. So, how do you check some ideal is unit ideal or non-unit ideal? So, an ideal in the ring A is a unit ideal if A equal to the whole ring A, and that is equivalent to saying equivalently some U belongs to A for some unit U in A, because once U belongs, then it has the inverse, and if I multiply that inverse by U, then that will be 1, and then therefore 1 will belong here, and so it will be equal. So, we just check this, this is obvious, but I would like you to keep checking things so that things become more and more easier. So, another last observation, a ring A is a field if and only if A has exactly two ideals. One is 0, 0 means the singleton 0. This is obviously an ideal and the unit ideal. These are the only two ideals because it is a field. Once it is a field, every non-zero element is a unit. So, if you have a non-zero ideal, it will contain a unit, and therefore, by above observation it is a unit ideal. Conversely, if there are only two ideals, any non-zero element will generate a unit ideal, because it is a non-zero ideal, and therefore, if A equal to AA, that is equivalent to saying A is a unit. All these are easy things to check. So, I will leave it for you to check this thing, and I will stop for this half, and we should continue after the break. Thank you.